Benzene has a molecular formula of C6H6. For many years, chemists were baffled about its structural formula. Kekulé is the first to depict benzene as alternating double and single carbon-carbon bonds in a ring. These carbon-carbon bonds were later found out to have similar bond lengths. The bond length is in between the lengths of single bonds and double bonds. This can be explained by the localization of electrons around the ring, and it's common for us to see benzene being depicted with a ring in the middle to represent the localization. Benzene forms only one monosubstitution product. That is, if you place a fluoro group at any point of the ring, it will be identified as a single compound. It only forms only one 1,2 disubstitution product. That is, if you place two fluoro groups that are adjacent to each other, whether you place it in double bonded carbons or carbons that are connected by single bonds, our instruments will only identify them as a single compound. It means that all 6 carbons and all 6 hydrogens of benzene are equivalent. Benzene does not react like an alkene. Alkenes react by electrophilic addition, for example, hydrohalogenation or acid-catalyzed hydration. These types of reactions do not occur in benzene. Benzene prefers substitution over addition. Benzene is also not readily oxidized or reduced. You will need harsh reagents or harsh conditions to affect these types of reactions. Before we move on to some properties of benzene, I will first discuss resonance. According to IUPAC, resonance is a representation of the electronic structure of a molecular entity in terms of contributing structures. Resonance also refers to the localization itself. As shown here, for example, is the structure of the carbonate ion. The carbonate ion can also be depicted without the lone pairs, and when the electrons in the single bonded oxygen move and is delocalized among different atoms, you will form different resonance structures. These resonance structures can be represented by a hybrid, and this hybrid structure has lower energy than any of the single contributing forms. In making resonance structures, only electrons of multiple bonds, such as double bonds, and non-bonding electrons can be moved. For example, the non-bonding electrons here in oxygen. Contributing forms must be proper Lewis structures, and more stable resonance forms contribute more to the structure of the real molecule. What are the more stable resonance forms? The most important resonance forms are those with more covalent bonds. The example I have here is 1,3-butadiene. If we move electrons to form other resonance structures, you will get this resonance form here. If we are to compare these two structures in terms of the number of bonds, the first one on the left will have more covalent bonds, and thus it should be the more important resonance form. Another criteria is that those in which all atoms have complete valence shell of electrons are more important. In this example, this carbon has only 6 electrons and does not satisfy the octet rule. If we move lone pairs from oxygen towards this position, you will form a structure wherein this carbon has a complete valence shell of electrons. There would be a positive charge on oxygen, but the stabilization that is given to carbon will contribute more to its stability. Thus, this structure here is more important. Those with no or minimal separation of charge are more important. Again, going back to 1,3-butadiene, this structure here does not have atoms with formal negative or positive charges compared to this resonance form here. Thus, again, this structure is more important. Those with negative charge on more electronegative atoms and those with positive charge on less electronegative atoms are more important. This example here shows a negative charge on carbon, and if you move electrons going to oxygen, you will get another resonance form wherein the negative charge is on oxygen. They seem to be similar in terms of number of bonds, but given that oxygen here has a negative charge and being more electronegative makes this compound here the more important resonance form. Single bonds with atoms involved in important resonance forms have restricted rotations. Using sophisticated instruments such as NMR, which measures environments between atoms, this bond between carbon and nitrogen has been found to have restricted rotation. This is because of the lone pair of nitrogen being delocalized in the structure. When 1 mole of cyclohexene is reduced by hydrogen in the presence of a metal catalyst to form cyclohexane, it released 120 kilojoules per mole of heat. Doing the same procedure with 1,3-cyclohexadiene, the amount of heat released is 232 kilojoules per mole. This compound also produced cyclohexane. Given these results, reduction of the diene produced about twice as much heat as the reduction of the cyclohexene. Thus, it seems reasonable to think that if you have a cyclohexatriene, the amount of heat that should be released is about 3 times that of cyclohexene, about 360 kilojoules per mole. However, when the heat of hydrogenation of benzene was measured, it is only about negative 208 kilojoules per mole. This is lower than what is expected, as it was concluded that benzene is 152 kilojoules per mole more stable than the hypothetical cyclohexatriene. This amount is resonance energy. The carbon central atoms of benzene are known to have sp2 hybridization. Each of these carbons can contribute a p orbital to the ring system and also 1 electron for each p orbital. It can be depicted where each carbon has a trigonal planar arrangement and the p orbitals being perpendicular to the plane of the molecule. Taking into consideration these 6 p orbitals, which if isolated we can draw in this manner. In the benzene structure, these 6 p orbitals with 1 electron each can be mixed to form molecular orbitals. Here we have bonding MOs and anti-bonding MOs. For a cyclic ring structure such as benzene, it is normal to see a molecular orbital present at the bottom, followed by doubly degenerate orbitals in the bonding and anti-bonding positions. We have 6 electrons being used and mixed. Thus, these 6 electrons will fill the low-lying orbitals. If you will see here in benzene, all these 6 electrons will occupy the bonding molecular orbitals. The anti-bonding molecular orbitals are all empty. On this basis, Haeckel formulated his rule for aromaticity. It states that planar monocyclic rings with a continuous system of p orbitals and 4n plus 2 pi electrons are aromatic. That is, if n is equal to 0, 1, 2, 3, etc. Which brings us to anilines. Anilines are monocyclic compounds with alternating double and single bonds. Benzene is an anilin and also this compound. Anilines are named using a number in brackets that indicates the ring size. Thus, for benzene, which contains 6 carbons, the name 6-anilin applies. It also means that this compound here, with 8 carbons with alternating double and single bonds, are best named as 8-anilin. These types of compounds can then be evaluated against Haeckel's rule. We know that 6-anilin is aromatic. It has a planar monocyclic ring, and it has a continuous system of p orbitals. All carbons are sp2 hybridized. The number of pi electrons in benzene is equal to 6. As 4n plus 2 being equal to 6 will give an n value of 1. How about 8-anilin? Does it satisfy Haeckel's rule? Let's take a look only at the number of electrons of 8-anilin. 8-anilin has 8 pi electrons. If you do 4n plus 2 equals 8, you will get n equal to 1.5. Thus, by that criteria alone, 8-anilin is not aromatic. 14 and 18 anilins are considered aromatic. This is 14-anilin. This is 18-anilin. All of these compounds are planar. They are monocyclic. They have continuous system of p orbitals. All of the carbons are sp2 hybridized. And if you will do the calculation, it has 4n plus 2 pi electrons. How do we know that something is aromatic? We have an NMR machine. NMR machine measures environments around protons and carbons, and it can easily identify diamagnetic currents that occur in these types of compounds. There are also aromatic ions, such as this compound. This is cyclopentadienyl anion. It has 2 pi bonds that contains 4 pi electrons and a lone pair here that is also occupying the p orbital. You should take note of this. If an atom with a lone pair is right next to an atom that is sp2 hybridized, this atom will also be sp2 hybridized. Thus, overall, this compound has 6 pi electrons. 6 pi electrons satisfy the 4n plus 2 requirement of Haeckel. This compound is monocyclic and also planar. And if this is an sp2 hybridized carbon, it also has a continuous system of p orbitals. Heterocyclic compounds can also be considered aromatic. For example, here is furan. Furan has 2 pi bonds containing 4 electrons plus an oxygen atom that contains lone pairs. Again, oxygen also assumes an sp2 hybridized character. Thus, one of these 2 lone pairs will be occupying its p orbitals, satisfying Haeckel's rule. Polycyclic aromatic compounds do not strictly follow Haeckel's rule. It contains more than one ring. However, if you would consider each ring This is aromatic. This ring is also aromatic. So are these rings. Thus, these types of compounds are also aromatic. The name of this compound is naphthalene for 2 aromatic rings fused together. For 3 aromatic rings, we can call them anthracene and phenanthrene. Azulene is a non-benzenoid aromatic compound. This compound may not look aromatic at first glance, but in drawing other resonance forms of this compound, each of these rings can satisfy Haeckel's rule. I will leave this for you to try. Draw resonance structures of this compound and find structures wherein each ring is aromatic.